refinement and revision of robot control programs based on prediction of what will happen and when these programs get executed. So just an example of what we want to do. If we, for instance, predict that an object that is carried slips out of the robot's gripper, we want to change the behavior of the robot so that the robot supports the slipping object with the other gripper, for instance. So here, as an example, this is, I think, more or less the way how most planning systems define their actions. This is basically an example for a pickup action and navigate action. So, and on the other hand, I have some videos. This is one, our new robot platform. So it's very early grasp experiment, but what you can see here is that the moved object touches this kind of tower of tea bags. So this is some behavior. It's caused by some inaccuracies during perception or execution of the action. So another example, it's our simulation. So what happens here is that the robot hits the cup with the other hand. So this is parallel execution of two actions that influence each other. And the final example, this is cutlery that is just placed correctly by the robot, and well, it slips out of the gripper and the robot has to retry again. So these are basically what we can see here is we have on the one side the logical description of actions, and on the other side how it's executed on the robotic system. So we have several sources of possible errors. We have inaccurate perception. We have maybe manipulation does not go completely right or something like this. And what we need to do in order to plan with taking into account all these possible sources of failure is we need to reason about all these continuous processes, about all the influences, so the processes that influence each other. Just consider the robot driving while moving its arm. So basically it's very hard to predict if the robot hits something or not. So basically what you would do is execute these actions sequentially in order to avoid. Another thing is we might have a discrepancy between the belief state of the robot and the reality. So basically what we can see here is the robot believes that it put the cup on the table, but actually what happened was the cup was put on the side of the plate. So this is something the robot believes to have done something right, but actually it did not. So this brings us to our approach. Basically what we do is we use simulation. We use a physically realistic simulation to predict the outcome of plans. We log everything that is simulated, and we make symbolic inferences based on this execution log. And finally, we use this information and this reasoning to improve plans. So another example, this is just some kind of an execution trace of a simple pick-and-place task or setting the table. So in natural language, I show here what some kind of conditions are we want to reason about. So for instance, we want to describe that the plate is on the cupboard at the beginning, or something like that the plate has been put down by the robot, that the plate is, after the put down action, is supported by the table, which means that the plate is on the table, or that, for instance, the robot cannot see the plate on the table because, for instance, its vision might be blocked by the robot's grip or something like this. Or another example, the robot believes that it placed the plate correctly on the table. So these are basically conditions we want to describe in our logic. Okay, so to summarize, what we want to do is we want to reason about, on the one side, states of the world. So what happened when the robot did some actions really in the world. So this includes location of the robot, this includes the location of objects, this includes force dynamic states, so contacts, supporting relations, which means that one object is standing on another one, or for instance, that two objects are attached to each other. For instance, the cup, when it's grasped, it's attached basically by the robot's gripper. And on the other side, we have the robot's belief state. So this includes the self-localization of the robot. This includes the perception of objects, the believed poses of objects, and so on. And finally, the third very important component is the plan execution. What we do is we not only log what happens in simulation, but we also log the execution of plans. So basically, we create a task tree. And this task tree contains information about intentions of the robot at specific points in time. And it allows us to relate plan steps to effects in plan execution in the physical world. So basically, we can infer plan steps that cause flaws in plan execution. So here is just an overview of our architecture. We have the two components. We have the plan interpretation and we have the environment simulation. And all information is just logged in an execution trace. So just simulation basically represents everything dynamic in the world. So it contains the location of objects, the real location of objects, the dynamic state of the world, of objects in there, so velocities, forces applied to objects, and so on. We have a list of collisions. So we need all contact. We know all contact points, and very important, we have simulation of sensors. So basically, we have on the one side sensor models that give us information about what the simulated sensor sees, can perceive, and on the other side, what really was there. So we have these two sides, what is measured and what should be there. And on the other side, we have the plan interpreter. The plan interpreter basically contains the complete belief state. So state variables and so on. So and during plan interpretation, every plan step, it's hierarchically structured task structure. So during plan interpretation, a task tree is created. We have child and parent relation in there, and we have access to the local variables of the plan. So basically, they are control programs and contain variables. We have access to all this information. We have status transitions, so when a task gets into the state of running, into failure state, or into a done state, or something like this. And we have the complete task expression. And it's very important because this task tree lets us to relate intentions or contains information about intentions. So I will come back to this in a few slides later. Basically, what we need to reason about all this plan execution is we need several concepts for it. So we define events, we define occasions, we define the intention and the purpose of tasks, and we need a causing relation in order to find out tasks that caused a specific event that is unwanted or something like this. So let me start. We have occasions and events. Events are basically occur at a specific point in time, and we make one assumption here. Events are always caused by actions of the robot, so we do not use any exogenous events that are created by the environment or by human acting in the environment or something like this. We assume here that the robot is responsible for every event. This is important for now because this allows us to really relate effects to a control program. Events basically describe the transitions between states in the world, and well, examples include picked up or the collision that happens between objects when it starts to happen, or another event is when the collision ends, or perception creates an event, an object perceived event. And to reason about these events, we define the predicate occurs. Occurs gets an event specification plus a time specification. On the other hand, we have occasions. Occasions are basically states that hold at points in time or at intervals in time. So actually, occasions can hold at a specific time point. They can hold at some point during some interval or throughout a complete interval of time. Examples include contact between objects, the location of an object at some time specification, or also object in hand. So when grasping an object after a picked up action, normally the condition object in hand should hold. To reason about occasions, we define the predicate holds. So next is, as already mentioned, we clearly distinguish between belief state and the world state. This is in our reasoning engine represented by two functions. To reason about the belief state, we use the function variable value at to get the value of a state variable or some other internal value variable in the interpreter at a specific time point. On the other hand, the world state, represented by the simulation, is accessed by the function simulator value at. Basically the same, but for more or less continuous processes in the simulation. And because of this separation of world state and belief state, we have two versions of the predicates hold and occurs. Basically, one version for the belief state, and on the other hand, the other version for the world state. And here's just an example. So the pose of the robot, the location of the robot at a specific time point, can be described by this. On the one side within the world state, and other side in the belief state. So the next thing is, now we come to the task tree. As already mentioned, plan interpretation creates a task tree. The intention of a task is can be inferred from when specifying a plan. It's basically, a plan is a control program, but with additional information. And this additional information contains the intention of this specific task. This plan can, or is normally hierarchically destructured, and executes some other tasks, so achieves achieves some other conditions in the world. We specify these intentions by using achieve. So whenever you program a control, you specify a control program, you specify the intention of this specific control program by saying achieve and then an occasion that is to be achieved. And this goal is basically then successful when, after executing it, this condition holds at the end. So this is basically how we can infer the correct execution of a task. So, finally we have the causing relation. We have to define, at least for the lowest level of our task hierarchy, the effects, the events that are caused by these tasks. So this is basically a definition of that an object in hand achievement, which means basically to grasp an object, have the object in the hand, causes a picked up event. So this means at the end of this task, the picked up event occurs. So now we come back to the examples of the beginning. We now have defined some logical formalisms to describe actually these conditions in the world. So basically the first one is the location is on the cupboard at time point 0. The next example is that the robot put down the plate on the table, so it executed basically the action to achieve that the location of the plate is on the table, and it believes that the location of the plate is really on the table. And the other examples are now specified like this. It occurs that we put down event occurs of the plate at time t, or that at time t the plate is supported by the table, so basically it's standing on the table, or that it does not hold that the object plate is visible at time t. So this is basically how we can express this. So now we can use this, of course. We can use this for diagnosing unexpected events, for instance. So basically, because we define what events are expected for the lowest level of task execution, we know at every time point which events are expected at this time point. So we can infer unexpected events. Basically all events that are not in this list. We can infer the effects of simultaneous actions. So remember the example of at the beginning where the robot just hit the cup and the cup fell out of the gripper. This is something when by simulating it we have an unexpected collision and the cup is lying on the ground at the end. So this is something that needs closer investigation and we need to fix this. The next thing is we can diagnose incorrect beliefs. I think this is a very interesting thing because since we have sensor models and we know what's happening in the world, we can find out if there is a discrepancy, and if there is, we can change the plan, for instance, to change its location to have a better position to look at an object or something like this. Next thing is we can find out not achieved goals. So basically we can find out situations where the plan basically failed without the robot plan interpreter itself finding out this failure. So basically we can predict failures that happen and cannot be predicted by the robot itself. And finally we used this for plan debugging by plan transformations. What we basically did was we were importing a plan from wikihow.com, and well, it just was a sequence of actions in natural language, and we turned this into a sequence of achieve statements and executed this. Well, the whole plan was under-parameterized, so it clearly cannot work at all without any plan debugging. But we could apply these reasoning mechanisms and transform plans in order to transform this plan. And finally, we could make it run, at least in simulation, because our real robot does not have all capabilities currently that are needed to achieve this table setting task. But basically, it's very promising. So now, to conclude, we have built a temporal projection mechanism that is based on realistic simulation that uses a physics engine. We create a sub-symbolic execution trace from this. So basically, we sample over the positions of objects and so on, and save this. We compute predicates from this execution trace, and finally we define some formalisms to reason about plan execution. Thank you very much. No, what we basically...
Why don't you use actually this information to put it in the
Well, actually, this slippage information, for instance, is basically coming for free because I think nearly everybody who is currently developing software for robots and doing robotics in such an environment like a human household or something like this is already using a simulation environment. So there is Gazebo, for instance, there is for the HRP2 or some things, and so on. And basically what we do here is we just use this simulation and extend it to save the information and use this information to reason about it. So this is basically something that comes for free.
We are going to put some uncertainty in this simulator to simulate the fact that actions are not
well, the uncertainty is basically in the sensor models. So this is something, sensors are basically also represented in the simulator. We have laser sensors based on rendering, and there is noise applied on this and so on. So this is basically these are models that don't come from this planning side, but more from the development of the robot control, the lower level and so on. Well, the big problem currently is speed, so we cannot use this for real-time planning. This is basically what we need to do is some sampling. Basically, but simulation is currently a little bit too slow. So sampling takes a lot of time, but actually the plan is to sample through plan execution. So we execute the same plan again and again and get a distribution of possible flaws that need more investigation. So this is the idea, but simulation, well, it's about real time or even a little bit slower. So we clearly need to improve this to real sampling. So actually, my dream would be to have something that plans in real time in parallel to plan execution, but this is not possible with the simulation we currently have.
Did you actually try the HRP simulator?
No.
It's a very good physical simulator. They're actually able to simulate sleep rates and stuff like that.
Yeah, currently we are using ODE, but...
Yeah, that's
So what's the advantage of using about these execution failures at the high level?
Well, consider an example where the robot opens a door, and by this opening of the door causes a blockage of some other location. So some optimization, if the robot has to get out several objects from a cupboard, for instance, to open the door just once, take the objects out and close the door later. So if if it needs one object, needs to do something else and needs another object, this optimization might not be so good. So basically the door might block something. So we have on the one side the low-level execution side, and on the other side the task side. And it's I think very hard to put this information that a door, the spatial information that a door might block another goal. It might be quite hard to put all this information, all possible cases that can happen if you execute a goal on the high level, into the reasoning, into the specification of actions. We get this for free when using simulation. We do not need to define anything here. We just execute and see it.
And it's more efficient to produce a better plan, which is going to keep and having control. Another last question?
Takes a long time to use physics simulations, but for instance, for the word thing, you really don't need geometry there.
Right.
Instead of just using a geometry-only simulation to do it like this, you use sample.
Well, basically, these were just first experiments with the simulation, but actually the plan is to go away from this extremely expensive simulation. I think a lot of time is wasted in rendering and the simulation of sensors. I think basically the best way to go would be to learn models for sensors that are very, very fast. So just to know how probable it is that the outcome of the sensor is this and this, and to use this geometry reasoning approach to reason about collision and stuff like this. So it's basically an idea, but this is future work, and I will work on this.
Very
you very much.